No problem. So if you don't mind, I'll start this. Okay. Hello, everyone. My name is Yazdani. I'm associate professor in aerospace structure at the University of London, formerly at Cranfield University, and at the moment actually work full-time in City University of London, but I'm a visiting academic at Cranfield University as well, which I do research and research supervision. Of course, I've got some holdings, some of these affiliation from the UK Institution of Mechanical Engineers, IMEC, and also the member of the European Society for Composite Materials. So my talk is mainly about future integrated civil aerospace, smart, clean, and faster and cheaper. And of course, this is something that I captured from my abstract. I want to draw your attention towards this again, that we're moving towards the futuristic integrated structures, and despite the ambitious and adventurous look in the future, there are still challenges to overcome. But everything looks very promising for future aerospace at the moment. Okay, so I'm gonna just come up with an agenda that I will actually outline some of the urgent needs and actually explain a little bit on the state of the arts in this area. I'll talk about integrity compromise upon integration in aerospace and integrity improvements possibilities, mainly on new adventurous talks rather than the mature, already well-developed technologies. Moving to faster and less technologies, and the research that we have been carrying out for years, and also the possibility of embedment of multifunctional composite for improvements. So, of course, there's a huge push towards metrology, especially in the area of structural health monitoring or SHM, and that's where probably this talk will be more relevant to this conference when I talk about towards AR-equipped structural health monitoring. So let's start. That's where we're at. That's actually one of the main motivation or inspiration, mainly for the push towards or need for eco-friendly, sustainable, and smarter aerospace and aviation. And what we are about to experience hasn't been experienced for about, let's say, 3 million years in terms of the temperature rise and the effect it will have on the climate change, and we're actually going through already year by year, and sometimes month by month we're experiencing that. And that's where actually we need, let's say, clean energy equipped transport, integrated light structures in transport, in-flight connectivity, eco-friendliness, and cost-effectiveness, of course, for development of anything processes in terms of integration, assembly, and manufacturing. So that will bring up an academy. Most of the talks is going to be that, okay, so if you're going to bring up some new integration instrumentation technologies, what would be the science behind it? How we develop that? Have we got mature science backing up such integration instrumentation, or we actually need to develop a new direction to science, come up with the breakthrough innovation, and come up with a whatever eco-friendliness, aerostructure or smart that we need. This I've captured from the European Aviation Safety Agency report 2019, and I think they actually repeatedly put this in many reports annually they publish that. And the whole message is here. That's the schematic for 1 hour flight of a 2-engine civil aircraft, let's say 150 to 200 passengers on board. And for 1 hour flight, let's say for about 1,000 kilometers, you will the engine or the aircraft will emit about 8.5 tons of carbon dioxide into the stratosphere, which is a sensitive layer of the atmosphere, and that's the main reason that it is causing climate change. This is before coronavirus, but if you capture a flight radar snapshot from removal, you see how catastrophic it can be if you multiply that effect of 8.5 tons of CO2 by the number of aircraft and by the number of hours flights. So it's quite a catastrophe at the moment. That is great that we got urgent actions in place, like the Paris Agreement 2015 on the climate change and European regulations related to a reduction, significant reduction of CO2 in any transport structures, let's say. And that's actually a very good, clear message. The top level leaders of the world come together for the first time, probably in the world, to talk, have a very unique voice in terms of taking necessary climate change actions to avoid the next extinction, let's say, for many species on the world. And of course, on the UK support as well, we got this Jet Zero plan by the council, and there are clear moves and developments we got in the UK. Loads of the panels, if you go on the Google, that's publicly available. You will see the panel's member, almost all of the serious aerospace and aviation industry are on board in the panel and chairs for Jet Zero plan to create a net zero carbon emission flight by 2050. And that's actually everywhere for every government. They're actually taking most of the governments getting that one. There are some good news already. It's been out for about, I think, 3 weeks or 4 weeks ago. We got this very, very good news from Airbus that they're moving with a new fleet of zero emission flights, let's say 0E, by 2035, which is great news for everyone working in this area. It will bring up a push towards new technologies and new, of course, pioneering activities that bring up new kind of job creation and everything. So it's a great push generally from both industrial, economical, and also the societal point of view. These fleets will be equipped with hydrogen propulsions called the Zero-E concept aircraft. We're not too far from that. This is not something that has been developed overnight. For decades, people have been working on such concept, and we also in academy we work on the development of new technology, and that doesn't only bring up technologies related to materials development and manufacturing development. It's about instrumentation and come up with the digitalization technologies as well. So there's a lot of talk on the autonomous vehicles and AI, and where we're at in this conference, and this might be relevant. The AR-equipped technology that can help us to make up not only eco-friendly structures for transport, especially for aerospace, we can make them smart and autonomous as well. I have been honored to work for quite a few years on this very ambitious project. That's one example that these movements have started decades ago. This Maximus project, if you Google that, is short for more affordable aircraft through extended, integrated, and mature numerical sizing. So look at the size of this project, and it's just one of the example of the Horizon 2020 European Council funds from thousands. Okay, so 57 partners across Europe for more than about 8 years of research working on this Maximus project, led by Airbus, including both academy and industries, and of course the public services and the regulatory sector. If we go back, focus on the aerospace, and we're talking about a highly integrated, highly conservative sector here, structure. It's actually an aircraft, let's say a civil aircraft, has been comprised of millions of parts, all right? And this is an amazing structure already. Okay, so lots of assemblies already existing, and one of the more focus of my research is a composite assembly, or composite joints, which comes not to be joined to another composite part. It can be a metal part, or it can be other like plastic part or something like that. In both primary, it's interesting, in both primary and secondary structures of an aircraft. And it doesn't mean it's not, it doesn't have challenges. It's got loads of challenges when you come up with an assembly. Either that you go bolting, you go riveting, you come up with bonding structure, especially for the secondary structure, and especially for composite repair assembly, let's say in the MRO. There's lots of challenges that have to come up with the highest integration possible. Look at this aircraft, the A350, very successful composite aircraft developed by Airbus. 53% of weight fraction of this aircraft is by carbon fiber. And you're going to come up with and imagine that that's kind of one of the early aircraft design that they actually developed composite for primer structures. So so how you actually come up with a very highly integrated structures of these aircraft, so to avoid some damages. And it's not going to be damage like on the ground only when things happen in the MRO, like a ground vehicle at the bottom image, for example. It might be damages from the lightning strike, might be damage bird strike simulation. Bird strike events that might happen during spatially taking off and landing, but also in service. You may this is a very, very common subject area that designers, the aerodynamicists, are designing for, are the flutter. So what flutter might cause on a composite aircraft or a highly integrated composite metallic assembly aircraft, you're going to move towards these eco-friendly structures. So these sort of things can be very catastrophic in terms of the life cycle of the aircraft, all right? But you may not end up with having a very catastrophic failure, or you may not have an event that causes catastrophic failure. You may have an impact damage, which is called a low velocity impact damage that may induce barely visible impact damage inside. And that can still be exceeding the designated extension area in the SRM, for example, the structural repair manual. And that might cause, I mean, future, if that's barely visible, if that's not detected properly, you don't know exactly where that's been tipped or tapped, right? Your specimen, because you don't see that much in 10 joules or 20 joules. But when you do, if you know where it's been tapped, if you do the CT scanning on X-ray, you would see the extent of the damage, right? And that's where still a repair becomes very, very important. And repair, mainly for composite aircraft, has got loads of challenges because you don't want to put a bolt inside, right? A primary structure, which is carbon fiber, or the toughened material like the M21, the epoxy material in A350. And so what you're going to do is actually you're going to take care of it by bonding, and that's mainly bonded assembly. So new concept is saying that, okay, how much of this damage that you see is dissipating the impact energy, let's say the majority of the impact energy. So based on my research and my colleagues' research, more than about 60% impact energy is dissipated by interlaminar delamination in laminated composites. And you can slightly extend it to bond assembly as well, that you have two polymer resins molecularly bonding together. So that's where this concept of the through the thickness reinforcement come in place as well to avoid such impact dissipation. We have, of course, examined that with the let's say industrialized already, for example, in DLR, that they work on development of the robotic or automated toe placement of composite periphery. So we have that examined. You will still get to see some extent of the damage in terms of interlaminar delamination. One of the base amazing, let's say, technologies that have come and have been developed by Boeing was the development of the Dreamliner B787. An amazing, magnificent, huge filament winding facility that they actually put the different parts of the fuselage all together, wholly integrated, rather than coming up with the pre-preg manufacturing or pre-preg laminate manufacturing, let's say, or automated placement. And in that technology, they did the filament of the carbon fiber totally continuous in different directions across the huge structure of the B787, which was partially cured with the resin, and then they put the whole structure inside a huge autoclave facility. So that's the extent of, that's the scale of the highly integration that we talk about, especially for lightweight critical structures like civil aircraft made by composites. But in the assembly, there are different phenomena happening. So we got, as I said, mainly dealing with bolted structures and bonded structures. The message here is that the damage mechanism introduced in different type of assembly is different from one another. Okay, And mainly because you're not dealing with the centuries of maturely developed aluminium aircraft. We're dealing with such shape that you see the computed tomography image at the bottom explicitly says the uncertainties across a cross section of a composite laminate. So you deal with loads of localized uncertainties at each location. You might have totally different properties rather than a homogeneous isotropic property that you may have in an aluminium aircraft. Still a lot of challenges. Once you actually introduce one thing there in the middle of the uncertainty, you induce a new complexity into this structure. That's what should be taken care of in every kind of design assembly to meet the design limit load, let's say in aerospace. And one of the challenges again, so once the damage has happened and it is repairable, that's the extent of the repair that you may go. So the market grows, the worth of the market in terms of the turnover is about $22 billion, right? And that's the scale. It's like a clean room. If you see the top left image, you have to avoid any kind of contamination on moisture or dust in the air to get involved in the polymerization, because you're actually working with something which is vulnerable, susceptible to moisture absorption, and that's polymer. If you're going to do bonding, let's say, if you're going to go cookie ring, something like that. Of course, there are some other technologies available at the moment for a small size of damage, like the right-hand image, like the Heiko innovation for a protective environment, and also the brilliant CARE project, which was led by Lufthansa Technik. I just took this image in 2016, but I think that the project started way years before that, when again the regulators like AISI was guiding through Lufthansa Technik and many companies attached to that to come up with a fully automated bonded assembly for comes the repair process. So I actually highly encourage you to look at the CARE project in future. We have done some activities as well to come up with the highly integrated structure, not having a single bolt or fastener. So that's sort of the fastener technology. The person you see is doing is our brilliant senior technician, Jim Hurley, who's been experiencing in the composite for about 30 years, 3 decades of experience. And we came up with this wing box demonstrator throughout the Flavir project, which I started probably 10 years ago. On the bottom side, at the top side, you see this the cross section of this wing box demonstrator, fully made, highly integrated, and you know what? It worked very well. Another project at Cranfield University, the Flavir project, or called shortly Flapless Air Vehicle Integrated Industrial Research. That's again was looking at making military UAVs made of highly integrated composites, fully composites, either in the ribs and the struts inside, and or in the skin of wings or the fuselage. So that went very well as well, and you can actually look up the video of being successful in terms of the flight. At the civil aircraft, of course, people are looking at the automated. This is the state-of-the-art concept already developed. Why that's a schematic? Because that's in the Clean Sky project, for example, right? And we're actually waiting for this. The world is waiting for this to be developed and come up with the half-shell longitudinal joining structure. If you visited by any chance Safran Composite in south of Paris, that I did last year, you might see a 6-axis amazing robot for taking control of the thickness of the bonding throughout a composite-to-metal or composite-to-composite bonded assembly. That's the level, that's the scale that we're looking at to avoid any human error, avoid any contamination, avoid any uncertainties induced in large structures. That's another concept taken from Clean Sky last year. Airbus Space and Defence, that was actually this year CFP 11, I think, call of the Clean Sky. Airbus Space and Defence is looking for technology that can manufacture a civil aircraft wing made of longitudinally continuous carbon fibers on the skin, and inside chop fabric, adhesively manufactured or 3D printed, let's say, or 4D printed ribs, still composite but chop fabric ones. Both composite are thermoplastic, either on this skin and also in the ribs, and mainly because we can not only make it very eco-friendly and highly integrated, we can take advantage of already recycled chop fabric materials that they've been proven very, very useful in providing uniformly distribution of the properties called quasi-isotropic. So that the world is moving toward that, and there are amazing plans by 2035. And we have been actually working on some of these. We try actually to make this as smart as well. This is one of the projects I was leading, and that the main project was that, okay, looking at the kind of a structural scale, still in laboratory experimentation, and see if I can induce some functional nanomaterials. In my case was, for example, graphene and carbon nanotubes. Can I not only improve the structural integrity, can I induce some reliable measurement, especially for cyclic loading? And it went well, actually. We published some of the works as well in the Nature Scientific reports, reporting that at the structural scale, you would be able to achieve reliable measurement, especially at cyclic loading. And our cyclic loading was increasing loading as well. So it was not like a constant loading during the cycle. So we came up with a kind of a simplified process as well, because processing of a new mixture of material, let's say embedment of a functional nanomaterial inside a structural grade or aerospace grade epoxy material, is very, very difficult. And it's also induced kind of a new uncertainties in place, a different location across a large scale material. You might have different dispersion density and dispersion quality. That means that at different location, you might end up with different properties. For our case, for enabling strain sensing or smartness in this structure, it means different sensing or piezo-resistive or piezo-electricity property, okay? And that's where we actually reported on a very efficient process and interpretation techniques. And you may actually end up with having have a look at this Nature Scientific Reports paper that we published this year, and see that we came up with an interpretation technique of using this carbon nanotube embedded adhesive for a bonded assembly and still be reliable for a structural scale, for cyclically loading and cyclically increasing for detection of adhesive bond defect. And that's one of the challenges in aerospace industry for bonded assembly as well, because you may induce zero thickness defect during a process, either because of not taking care of the process parameters very much, or also because of contamination being involved. So you might end up having zero thickness defects, but the problem is that it's very, very difficult to identify that defect or detect that defect using non-destructive inspection. Once that's made and part of the structure, you cannot cut it out and then examine it, right? And that is why it makes it very reliable in terms of NDT technologies being able to detect such zero thickness defects. So we say that if we actually embed such a smartness entitled material, come up with a new interpretation technique, we will get some reliable signals of when the adhesion is going to be fade. But I'm going to show you the challenge right now in this video. Okay, we're showing that the system is working properly. Okay, so we can extend it using the proposed embedment technique that that's in the journal paper. But look what's going on here. Let me just move it down. Yeah, okay. A load of blah, blah. That's our specimen there, and we're looking at that with the laser extensometer for validation as well. But look what's going on. So we got the two probe technique, right, at the sides of the specimens connected. And it's going to be associated with loads of electronics as well. All right. So where are you going to put these electronics? How are they going to, this is a flat specimen. What if we got a kind of a non-flat specimen? How are you going actually to embed such technology in non-flat specimens? So that's one of the challenging. The scale of possibility is this. I would say it is very, very possible to take advantage of our continuous nanofiber production and make carbon sorry, yes, carbon nanotube at the scale of, at the diameter of 100 nanometers, but in meter lengths. Okay, and then actually fit that inside a tufting machine like this middle image, and program it to make a totally smart materials, highly reliable on every kind of a sample, either flat or non-flat specimens. All kind of smartness technologies, taking advantage of piezoelectricity, that's already out. And if you want to know where that's been used, in the piezoelectric sensors, right? So there's loads of sensors already developed, relying upon the piezoelectricity as a good property to give signals when your material is being deformed or damaged. But the thing is that once you actually use, for example, a PVDF material as a layoff inside, it actually, in terms of the thickness, is comparable, or is still considerable at the level of the thickness of a prepreg laminate. For example, if you got 200 microns, you might have about 100 microns or 50 microns of the thickness of the PVDF. So if you imagine you're going to lay it up over 32 plies, for example, for one section of A350, you're gonna add is, first of all, adding the thickness to that side of the composite component, and also you may add to the weight. But using electrospinning technique, that's what we introduce here, you may end up with having less than 1 micron thickness between each layer. So the smallest thickness that we could achieve using this technology, thanks to the industrial Monroe technology in the UK, who helped us for such research, we could achieve about 250 nanometers thickness. But let's say 1 micron, so that's nothing, almost, so almost zero weight penalty, almost zero thickness penalty. And we could achieve some reliable results, and you can see at the ACS Omega publications for results. Generally, sorry about this word overlapping with the logo. Smartness versus structural integrity is always a big issue, and you have to actually take care of it once you actually use some functional nanomaterial, though they're very, very low weight, but they're very advantageous in enabling smartness in structures. But the thing is that they compromise the structural integrity. Again, if you're going to know how they easily compromise that structural integrity, you can have a look at our journal papers in the Journal of Polymers. Actually, that was ranked the second top highly cited papers last year in 2018 and 2019. This journal, Q1 journal, which we were so happy because it looked like the impact of our investigation have proven right. But they're very beneficial. We recently used that in a kind of an electric core application. We use carbon nanotube to adjust the coefficient of thermal expansion. There is a problem in electric core components. Let's say we got a lithium battery working. Everyone loves that. It's been developed for decades. We got the Nobel Prize last year for the lithium battery development. But that has to be stacked somewhere, right, inside a package, a component, and that's a hybrid composite metal joint, actually. So if we have a hybrid multi-material joint with different properties, significant coefficient of thermal expansion, imagine if the temperature of this lithium battery goes up to about 200 degrees centigrade, right? And you're going to take care of it. Of course, you take care of it with the cooling system. Well, what about the hybrid joints this lithium battery has been connected to, right? So the metal has got a very good, let's say, a desirable coefficient of thermal expansion, but generally composite, because they're made of the polymer, they're not very good thermally conductive. So we have been able to achieve, let's say, adjustment of these thermal properties using these functional nanomaterials as well, quite significantly. There's another technology that people are using a lot already, very well developed, and that's thermography, right? Laser shrink is another one. The CE scan is another one. You can send the ultrasonic test, so taking advantage of the sound speed variation inside the material to identify what is the damage. Thermography works based on that, but it works based on this thermal conductivity issue, and then it brings up a thermal decay. So it means that if you actually scan your image, like my image here, you would be able to see how the temperature, the heat energy is going inside your body. And it's actually very safe to do that. It's not unsafe, like something like laser shotography. And the new technology like a microwave non-destructive inspection being developed as well. One of the pioneers is Manchester University. They're very good as well, but I think one of the concerns about them would be the health and safety issues. But thermography have proven very right. And you know what? It's scalable. That's the wing box we developed, as I told you, at the Composites Center. That's been brought up in a very famous good lab developed for these pioneering technologies, smart technologies, let's say at Cranfield University. And that's me, of course, with my PhD, Shakib. So I was working actually to put the thermography camera on top of a UAV system. It's a very low-weight thermography camera. It's the size of a €2, let's say 2 pounds. And it can fly and actually take an image. Of course, consideration of all of this geometry constellation, also the things around moving this. And you would be able to see how you interpret the signal you receive from the energy decaying inside the structure to deformation, defect, and damage. That of course have been helped at just research with the University of Laval professors of your Maldoc's group, brilliant on signal to noise ratio for NDT diagnostics. We actually have been let's say lucky to see that kind of thermographic imaging innovation has gone into our Cranfield B737 aircraft. The one that's shown with the red arrow is the UAV moving around with the thermography image over this aircraft. It was not led by me. I was just there as an audience, let's say, but it was led by an Eagle Labs, which was very, very interesting. And you may actually look up the results as well at how you would be able to do that. Partially, it was funded by Airbus as well. So there are still things very useful, let's say, in aerospace industry in terms of taking advantage of contactless remote sensing. So how we would be able to do that without embedment of a sensor inside or over the surface of an aircraft. And that's one of the new, not very new, but I mean, it's one of the highly novel, still requiring research to be fully developed. One of the other techniques that we say might be useful was taking advantage of dielectric sensing. You come up with the steel horns antennas attached to a vector network analyzer and try to actually see how the material in terms of response is changing. That's relying not on the thermal conductivity, not on the sound distribution, but mainly on the high dielectric properties that are changing, right? And then we got kind of a sports and different areas. For this research, we said that, okay, so once we have a camera, for many actually type of research that we do, why not taking advantage of it for development of an augmented reality equipped composite assembly technique? I came with 2 different group and individual projects. I wish I had the image for you to actually mimic what has been done already in the Beautiful Care project using this. Care project has said that augmented reality has manifested that is brilliant for maintenance already. And it can significantly mitigate human error. And that's one of the issues, right? You're going to come up with, if you are a technician being trained in Boeing, for example, you come up with different kind of levels in being able to repair something, right? Or even remove the material. So the CARE project has taken care of even removing of the material with robotic material removal, mechanical removal technique. The main proposition here by the AR was that, okay, if you rely on geometric features, can we find out mechanical performance? Can we relate this kind of using the correlation analysis? If we have some visible features, can we identify invisible features that are lagging behind using NDIs, right? Like, as I said, the zero thickness defects that might apply in an bonded assembly or in composite plies, laminates. And that will, of course, if that's equipped with the regulations for the system, it can automatically lead to permit to fly. So we actually carried out 2 separate projects on augmented reality composite assembly and repair. And we used a tablet version for this, and some sort of, I think this looks amazing to us in our sector. Probably that's just a daily common practice for you guys working in VR and AR already. But for us, it was very exciting to see that it works using a HoloLens and game. And we took some of the demonstrators with the HoloLens, try actually to do a composite assembly. CAD were provided to match the direction of the fibers that we positioned on each of these plies. And it worked very well, actually. So we got one of the senior experts of the EAs on board and got comments on how actually our technology can be benefited further. So first of all, comments from the EAs are, this is a very good technology for process control in MRO for aerospace application. Data can be accessed to SRM automatically, and you don't need to go back and look at the SRM, come back in place like as a technician. So it's always there that you can see it visibly in front of your HoloLens. Data recording will be provided through this for parameter fly and other kind of fusion investigation. Remote real-time access might be enabled. And of course, that's in terms of the responsibility that will bring up some delegate responsibility in what has been done. Because this is a lay-up structure. This is a multi-layers. Once you have laid up, you wouldn't be able to see it until you cut section it. So you don't know what has happened until you see something step by step like this in here. So it's a great actually education tool as well. So we can bring students on board and try to exercise this to use our augmented reality tool for composite process. We went actually further, we stepped further and actually working with some of the colleagues already, some of the colleagues from SSVAR, to see if that's possible to embed such technology to look into a civil aircraft wing with the fluctuations or the oscillations of the end wings going meters or centimeters displacement, identify what are the surface data and then translate it to damage inside. That's one of the ideas that we're looking for called flow map SHM. Looking at the surface on the left-hand side and identify some features in the surface data, translate it to internal damage. Would that be possible? If that's possible, that will bring up a digital twin of aerospace aerostructure performance as well for future. And just don't forget there's a very, very complex damage mechanism and damage topology inside a composite layup. It's not a single damage. So can we actually translate that to this? And can we substitute this super complex sensor embedment technique that's already, I mean, I'm showing a PZT, a piezo transducer sensor here, but it can be any kind of strain gauges or sensors that you can put, for example, the fiber optic sensors. That's very well known to everyone that all of the sensor embodiment technologies they're along with the complex technique. And the problem is that once they damage, it's very difficult to repair. So once you actually put it, even if you're going to interpret the signal data, there are loads of consideration in place, and you may not even end up with having a reliable detection technique. So how we can AR introduce something that will be better? Look at the scale of the sensor embedment. That's the picture I took myself in 2019 JEC composite when everything was good and no one had mask. You see, for example, on the left-hand side, a scale of aerospace structure here, which has been zoomed on the right-hand side with many sensors, all right? And there were some innovation to say, okay, so let's embed such thing that we did with the PVDF material and the IDE electronics all over the place. So we know already it's this big, big challenge, and everyone knows that. So we think that if you come up with a contactless remote technology, that AR can also help for overlaying such information, additional information, that would be brilliant, and people are looking for that. That's just a summary of what I said in terms of proposing a structural health monitoring based on augmented reality, and this is an ongoing project at the moment that we hope actually to succeed to get the proof of concept of that. Thank you for your time, and I would be happy to answer any question.